Today we are going to learn about mastering Python threading with real-world examples. Discover how to effectively implement threading in Python applications to optimize performance, specifically for I/O-bound tasks, and enhance your programming skills.
Welcome to our session on mastering Python threading with real-world examples. Understanding threading is crucial for improving the performance of I/O-bound tasks in multi-core processors. In this introductory section, we will explore what threading is and why it is an important skill for Python developers. Threading allows you to manage multiple tasks concurrently, making it a powerful tool to optimize application performance. By the end of this video, you'll know how to implement threading efficiently. Let's dive into the world of Python threading and see how it can be applied in real-world scenarios. The Global Interpreter Lock, or GIL, is a fundamental concept in Python's threading model. It is a mutex that protects access to Python objects, preventing multiple native threads from executing simultaneously in Python's interpreter. This means that even with multiple threads, only one can execute Python bytecode at a time. While this may seem limiting, the GIL is necessary for Python's memory management. However, it can become a bottleneck in CPU-bound tasks. In this section, we'll explore the impact of the GIL on multi-threading and discuss strategies to mitigate its limitations, such as using multiprocessing or offloading CPU-bound tasks to external libraries. Understanding the GIL is essential for effectively implementing threading in Python. The threading module in Python provides a simple and efficient way to create and manage threads. To create a thread, you can either instantiate a thread object and pass a function to execute or subclass the thread class and override its run method. Starting a thread is as simple as calling the start method, which invokes the run method in a separate thread of control. Understanding the thread lifecycle, including creation, execution, and termination, is crucial for effective thread management. In this block, we'll walk through code examples demonstrating how to create and start threads using the threading module, which will serve as a foundation for building more complex multi-threaded applications.
Synchronization is key to ensuring that threads do not interfere with each other when accessing shared resources. Python's threading module provides several synchronization primitives, including lock, lock, and semaphore. A lock is a basic synchronization primitive that ensures only one thread can execute a critical section of code at a time. RLock, or reentrant lock, allows the same thread to acquire the lock multiple times, which is useful when you need recursion within a lock. Semaphores control access to a resource by a set number of threads. Understanding and using these synchronization tools is vital for avoiding race conditions and ensuring thread safety in your applications.
Managing the lifecycle of threads is crucial for efficient application performance. The join method is used to wait for a thread to complete its execution before continuing with the main program. This is particularly useful when you need to ensure all threads have finished before proceeding. Daemon threads, on the other hand, run in the background and are killed when the main program exits. They are useful for background tasks that do not need to complete before the program ends. In this section, we will explore how to use join and daemon threads effectively, providing code examples that demonstrate their practical applications in managing the thread lifecycle.
When multiple threads access shared resources, such as files or variables, it can lead to race conditions, where the outcome depends on the sequence or timing of threads. These conditions can cause unpredictable behavior and bugs in your programs. To avoid race conditions, it's essential to use locks and other synchronization mechanisms correctly. Deadlocks, a situation where two or more threads wait indefinitely for each other to release resources, should also be avoided. In this section, we will discuss the challenges associated with shared resources, explore race conditions, and provide strategies to handle these issues effectively, ensuring your multi-threaded applications run smoothly and predictably.
Inter-thread communication is crucial in multi-threaded applications to ensure threads can exchange data safely. Python's Q module provides a thread-safe FIFO implementation for managing shared data. It supports blocking and non-blocking operations, allowing threads to wait for data availability or proceed immediately. The producer-consumer pattern, where producer threads add data to the queue and consumer threads retrieve it, is a common use case for queues. In this block, we will explore how to implement thread-safe queues using the Q module, and demonstrate how to apply the producer-consumer pattern in practice, ensuring efficient and safe inter-thread communication.
In this practical example, we'll build a multi-threaded web scraper that demonstrates the application of threading concepts we've discussed. Web scraping often involves network I/O, making it an ideal candidate for threading to enhance performance. We'll use threads to concurrently download data from multiple URLs, improving the efficiency of our scraper. We'll also implement synchronization mechanisms to handle shared resources, such as the list of URLs and the downloaded data. This hands-on example will provide a comprehensive understanding of how to apply threading to real-world problems, showcasing the advantages of using threads to optimize I/O-bound tasks.
In conclusion, Mastering Python threading is a valuable skill for optimizing the performance of I/O-bound tasks. Throughout this video, we've explored the fundamentals of threading, including the impact of the GIL, creating and managing threads, synchronization techniques, and handling shared resources. We've also delved into practical applications, such as building a multi-threaded web scraper. By following best practices and understanding common pitfalls, you can effectively implement threading in your Python applications. Continue exploring threading with additional resources and practice to refine your skills. Thank you for joining us in this journey to master Python threading.